Word problems and calculations. Problem 1. Dorothy is assigned to make a soap for their consumer chemistry class. She wants to make soaps with sodium hydroxide because of its potential to alter fats. She also knows that sodium hydroxide is a common compound in household products like liquid drain cleaners. Dorothy wants to calculate the pOH of a sodium hydroxide solution with a concentration of 4 times 10 to the power of negative 3 moles per liter. First, let's write the given, which is the concentration of sodium hydroxide is equal to 4 times 10 raised to the power of negative 3 moles per liter of the solution. Next, pH is then calculated using the expression pOH equals negative logarithm times the given concentration in moles per liter. Solution. Using the calculator, we solve pOH equals negative logarithm of 4 times 10 raised to the power of negative 3. So the answer is 2.3979400009. And we round it off to the nearest hundreds, so the final answer is 2.40 moles of sodium hydroxide per liter. Problem 2. Wolf learned in the chemistry class that based on equilibrium concentrations of hydrogen ion and hydroxide in water, pH plus pOH equals 14, is used to convert between pH and pOH. He wanted to apply the equation to find the pH through solving the pOH only. The pOH of a sodium hydroxide solution with a concentration of 4 times 10 to the power of negative 3 moles per liter. So the pOH is already calculated in number 1, so let's just copy the whole calculation. Given, and the formula, we use a negative logarithm of the hydroxide ion and the pH plus pOH equals 14 for finding the pH. Solution. So we solve for it, and the negative logarithm of 4 times 10 to the power of negative 3 is equal to 2.40 moles of sodium hydroxide per liter. So now to find the pH, we use the formula pH plus pOH equals 14. We transpose pH is equal to 14 minus pOH. So pH is equal to 14 minus 2.40. So the pH is 11.6, and this indicates that the solution is basic. Problem 3. Potassium hydroxide is an odorless white or slightly yellow, flaky, or lumpy solid, which is often in water solution. It is used in making soap as an electrolyte in alkaline batteries and in electroplating, lithography, and paint varnish removers. Thus, ELISA wants to calculate the pH of a potassium hydroxide solution, which is 6.50 times 10 to the power of negative 3 moles of potassium hydroxide per liter for her laboratory experiment. First, let's write the given, which is the concentration of potassium hydroxide is equal to the 6.5 times 10 raised to the power of negative 3 moles per liter. So pH is then calculated using the formulas negative logarithm of the hydroxide ion and the pH plus pOH equals 14 for finding the pH. Using the calculator, we solve pOH equals negative log of 6.5 times 10 raised to the power of negative 3. So the answer is 2.187086643 as seen on the calculator. Thus, we round it off to the nearest hundreds. So the final answer is 2.19 moles of potassium hydroxide per liter. Now, to find the pH, we use the formula pH plus pOH equals 14. We transpose pH is equal to 14 minus pOH. So final answer is pH is equals to 11.81, and this indicates the solution is basic. Problem 4. The table salt is purified with hydrochloric acid. It's used to control the acidity of liquids. It's used to keep the pH of pharmaceuticals, meals, and drinking water in check. It is also used to clean up waste streams containing alkaline substances. Because Linda wants to find the pH of a 0.0025 moles of the aqueous solution of hydrochloric acid per liter. The hydrochloric acid is a strong acid and is 100% ionized in water. Because um, the concentration is 0.0025. So first, let's write the given 0.0025 moles of hydrochloric acid per liter of solution. Then we write the given hydrochloric acid is equals to 0.0025. Next, pH is then calculated using the expression pH equals negative logarithm of the hydrochloric acid concentration. Then, negative logarithm of 0.0025. Then, as seen in the calculator, the answer is 2.60205991. Therefore, the pH of 0.0025 hydrochloric acid is 2.60 moles of hydrochloric acid per liter. Problem 5. During their laboratory class, Martha was tasked by her professor to calculate the pOH of a 0.0235 moles of um, hydrochloric acid solution per liter. So first, let's write the given, which is the concentration of hydrochloric acid is equal to 0.0235 moles per liter. Next, pH is then calculated using the formulas negative logarithm of hydrogen ion and the pH plus pOH equals 14 for finding the pOH. By using the calculator, we solve pH equals negative logarithm of 0.0235. So the answer is 1.62893238 because we rounded off to the nearest hundred. So the final answer is 1.63 moles of hydrochloric acid per liter. Now to find the pOH, we use the formula pH plus pOH equals 14. We transpose pOH is equal to 14 minus pH. So the pOH is equal to 14 minus 1.63. So the final answer is 12.37. Next, worded problems involving preparation of buffer solution and or calculation using Henderson-Hasselbalch equation. Problem 1. Ammonia is also used as a refrigerant gas for purification of water supplies and in the manufacture of plastics, explosives, textiles, pesticides, dyes, and other chemicals. On the other hand, hydrogen bromide is used to make chemicals and drugs, as solvent, and as a veterinary drug. A chemist wants to calculate the pH when 50 ml of 0.180 moles of ammonia per liter is mixed with 5 ml of 0.360 moles of hydrogen bromide per liter. So, solution. First, we determine the moles of each substances. So, 0.180 mole per liter times 0.05 liter is equal to 0.009 mole of ammonia. Next, for hydrogen bromide, 0.360 mole per liter times 0.005 liter is equal to 0.0018 mole of hydrogen bromide. Second, ammonia and hydrogen bromide react in a 1:1 molar ratio. So we should determine the moles remaining after the reaction. So ammonia is 0.009 mole minus 0.00180 mole. So all in all, it's 0.072 mole. Third, the ammonia that reacts with the hydrogen bromide produces ammonium ion. From the chemical equation, ammonia plus hydrogen bromide is ammonium bromide. So we can see that the ammonium ion is produced in a 1:1 molar ratio with each reactant. Since hydrogen bromide is the limiting reagent, we determine that 0.0018 mole of ammonium ion will be produced. Thus, we may ignore the bromide since it plays no role in the pH. Or, so this is the Henderson-Hasselbalch equation to determine the pH. But first, let's find the pKa of ammonium ion. Fifth, I use the pKa of the ammonium ion in the Henderson-Hasselbalch equation. Here is how we determine the value. So, the Ka Kb is equals to the Kw multiplied by Ka times the 1.77 times 10 to the power of negative 5. So the answer is 1.0 times 10 to the negative 14. So the Ka is equal to 5.64972 times 10 to the power of negative 10. Because the pKa equals the negative logarithm of 5.64972 times 10 to the power of negative 10, as shown in the calculator. So the answer is 9.247973075, and we round it off, resulting to 9.248. So back to number 4, pH equals 9.248 plus the logarithm of 0.0720 over 0.0180. So the answer is 9.850. Problem: use the Henderson-Hasselbalch equation to calculate the ratio of bicarbonate to carbonic acid in normal blood, which has pH of 7.40. So to solve, we use the formula pKa equals negative logarithm of the Ka. First, the pKa is equal to negative logarithm of 4.2 times 10 to the power of negative 7. So as shown in the calculator, the answer is 6.37675071. And the final answer is 6.38. So second, acetate ion over acetic ion is equal to tan to the power of pH minus pKa. So tan to the power of 7.40 minus 6.38 is equal to 1.02, which is equal to 10.5. So the ratio is so high because blood needs to be able to neutralize more acid than base. That's because cellular metabolism produces acidic waste products that are pumped into the blood. Problem 3. A scientist wants to calculate the pH of a 0.5 liter of buffer solution composed of 0.700 moles of formic acid per liter and 0.5 moles of sodium per formic per liter. So first, we can use the given molarities in the Henderson-Hasselbalch equation. pH equals pKa plus the logarithm of base over acid. Because pH is equal to 3.752 plus the logarithm of 0.5 over 0.7. Because pH is equal to 3.752 plus negative 1.46. Thus the final answer is 3.606. But as shown in the calculator, the answer is 3.605871964, but we round it up to 3.606. Problem 4. A buffer is prepared by a student for their laboratory experiment in biochemistry containing 0.8 molar acetic acid and a 1.0 molar sodium acetate. What is its pH? So first, we use the Henderson-Hasselbalch equation. pH equals pTA plus the logarithm of base over acid. pH is equal to 4.752 plus the logarithm of 1 over 0.8 plus pH is equal to 4.752 plus 0.097. But as seen in the calculator, the answer is 4.8489100013. And we round it up, so the final answer is 4.849. Problem number 5. So problem number 5 is somewhat similar to number 4. The amount of acid was interchanged with the base. A buffer is prepared by a student for their laboratory experiment in biochemistry containing 1.0 molar acetic acid and 0.8 molar sodium acetate. What is its pH? So first, we use the Henderson-Hasselbalch equation just like the number 4. So pH is equal to pTA plus the logarithm of base over acid. Thus, x equals 4.752 plus the logarithm of 0.8 over 1. Thus, pH is equal to 4.752 minus 0.97. And as shown in the calculator, the answer is 4.65508987. We round it up, so the final answer is 4.655. That's all. Thank you.